In the last lecture, we were discussing about various non-idealities in a MOS capacitor system. We did talk about work function difference, fixed oxide charge and interface trap density and how it impacts the capacitance voltage characteristics. Today we will continue the discussion and look at some more non-idealities, and after that we will look at parameter extraction from a capacitance voltage characteristics. So, just to sort of recap what we have said earlier, if you have a p type substrate, then the capacitance versus voltage curve for an ideal situation will look like this, and if it is only fixed oxide charge, this will essentially shift to the left because fixed oxide charge is invariably positive. And on the other hand, if it is due to combination of both fixed oxide charge and interface trap, not only will there be a shift, but also there will be a stretch out, and that is what we said, the CV could probably get stretched out something like this, right. And this could be in the presence of both fixed oxide charge and interface trap density, depending on how much is the interface trap density and how much is the fixed oxide charge. Now, typically today, if you are looking at the silicon technology, silicon CMOS technology, we have figured out ways to really minimize both fixed oxide charge and interface trap density. Today routinely we get the fixed oxide charge in the range of less than 10 power 10 per centimeter square. Okay, this is number. If you want to actually get the charge, you multiply with Q, that gives you the charge. Okay. And similarly, the DIT, that is interface trap density, could also be of the order of 10 power 10 per centimeter square. This is the kind of technology that we have, but in the olden days, in the early days of silicon technology, this used to be very high, in the range of 10 power 11, 10 power 12 per centimeter square kind of numbers, right. Those were very high numbers, but we have come up with various process techniques to overcome all these issues. Okay. And one other thing that of course, if you start looking at some other dielectric, not silicon oxide on silicon, if you are developing a new dielectric, then of course you could start with very high trap density, then you need to optimize the process to minimize those trap density. Similarly, today we are talking of building transistors on different substrate like germanium or compound semiconductors. Even there, when you put an insulator on top of such a semiconductor, your trap density may not be 10 power 10. Your trap density, not surprisingly, will be in the range of 10 power 11, 10 power 12 kind of numbers, but then you need to optimize it and bring it down to these numbers if it has to compete with the kind of technology that silicon has today. Okay. Now, in the context of fixed traps and interface traps, there is one other kind of non-idealities, which is what is called slow interface traps. Okay. Now, just quickly look at this. Typically, in a silicon oxide system, you will not see this slow interface traps. Okay. What it means is that it is not quite interface trap, but it is not also fixed charge. It does vary, but it varies slowly. Okay. Now, what is the implication of that? The slow interface traps could lead to what is known as hysteresis in CV characteristics. Okay. Now, when I say slow, I need to sort of qualify that statement. Okay. When I talk of interface traps, I did tell you that interface traps do respond to the slow varying, the signal that is applied to the gate if it is slow varying. That is because they have certain time constants to interact with the channel charge, so that they can exchange charge. Okay. Typically, the interface charge traps that we have, they have time constants anywhere from microsecond to millisecond, maybe a few tenths of millisecond. Okay. And that is why we call them they are fairly fast. But if you have on the other hand, if you talk of fixed charge, it has time constant which is sort of infinite, meaning it does not really change, right. Once it is positive, it just stays positive, it does not get discharged and become neutral, you see, that is another extreme. But if your oxide that you have put in has some extra defects, they may not be exactly at the interface, maybe little away from the interface, hence the time constant is little slower. Okay. Then you may have what are called slow traps, and which may have their time constants in a few seconds, okay, a few seconds. Now, what is the implication of this, right? Typically, whenever you do a CV characteristic, right, that is capacitance versus voltage characteristics, you can sweep the gate voltage either from negative voltage to positive voltage or from positive voltage to the negative voltage, and you can do both, in which it is called a bidirectional CV characteristics, right. I have swept the voltage from negative to positive and come back from positive to negative. Okay. So, ideally if you do this in the forward direction, if your CV looks like this, in the reverse direction the CV will essentially overlap on top of it. This is what you will have ideally. Okay. Indeed, this is what you will have in most of the silicon devices today. You will never see any hysteresis, that is forward and reverse CV are identical. Okay. Now, this will happen if you have fixed charge, even if you have interface state traps, they will not really fast interface traps, that is they will not really give rise to any hysteresis, okay, because they are responding, typically the CV measurement time frames are few seconds, right. Maybe you go back here from minus 5 volt to plus 5 volt, let us say that may take a few seconds, and then you start coming back. Okay, that is how your CV characteristic would look. Okay. Now, what happens with the slow interface traps is that they do not respond during the CV sweep, because that sweep is reasonably fast for them. Okay. But once you are here, you are essentially spending time, once you reach this band bending, the band bending does not change in inversion, it is more or less constant, and similarly the band bending in accumulation is also more or less constant. Okay. Now, going up dial days, coming back like this will be a matter of a few seconds. During this time they would respond, meaning only at this extreme and at this extreme they will respond, okay, because they are relatively slow, they do not respond during the CV sweep. Okay. So, what I mean by that, again recall our discussion, at this point our band bending will look something like this, this is Fermi level, okay, accumulation condition. At this time the band bending will look like this, inversion condition, remember, okay. And here ideally all these traps should be empty and all these traps should be filled, correct, because below this Fermi level, that is what we are looking at. Okay. But what happens with respect to these so called slow traps, they may not be exactly at the interface, but they may be little bit away from this interface, let us say somewhere here, and hence they take little longer time to respond. They also respond to the level of Fermi level position that you have. Okay. So, what happens is that let us say out here you have all the traps empty, okay, and when you come here you fill all these traps, right, with the electrons. Okay. And now when you are going back you have those extra charges in these traps, okay, and these extra charges stay put when you are doing this CV sweep, right. So, because you have these extra traps, extra charge, in this case when I have come from negative to positive, I have this condition, and when I am waiting here during this period and while I am coming back, all these are now filled with electrons. Okay. Now, you see when I am going back I have extra negative charge here, and because there is an extra negative charge the CV will not trace the original CV, the CV will actually go back like this. Why go back like this? Because there is an extra negative charge, whenever there is an extra negative charge the curve shifts to the right, okay. If there is extra positive charge the curve shifts to the left, okay. So, it goes back like this. In other words, forward sweep will be like this, a reverse sweep will be like this, and hence there is what is called a hysteresis. Okay. And whenever there are slow interface traps the hysteresis is always counterclockwise, notice here, while you were coming here the CV was like this, and at this extreme you filled lot of electrons here and the charge is negative, and hence it went in here, and here you have lot of positive charge, the CV will come here and so on and so forth. So, whenever first of all if you see a hysteresis in CV characteristic, that is indicative of the fact that there are so called slow interface traps, which is also not good, just as fast interface traps are not good, even slow interface traps are not good. And if the hysteresis is counterclockwise, that is clearly a signature of the hysteresis is coming due to slow interface traits. Okay. And it turns out you could also have hysteresis, which we rarely have, unless today we take lot of care in making sure that there are no impurities in terms of so called mobile ions such as sodium, potassium and so on and so forth, right. If you have mobile ions, then you can also have a hysteresis which is called clockwise hysteresis. Hysteresis will not be a counterclockwise hysteresis, a hysteresis will be a clockwise hysteresis. So, clockwise hysteresis is not an indication of slow interface traps. Okay. Whereas, if you have slow interface traps, there is going to be hysteresis, and that is always going to be counterclockwise as we discussed. Okay. Now, at this point it may be worthwhile to also discuss the non-idealities of mobile ion charge, which as I said is very rare, but again if you mess up with your cleaning procedure and instead of taking quartz ware you take a Pyrex glass to clean your device silicon. Pyrex is a very good contaminant of sodium and potassium, right. When we talk of mobile ion charge in oxide, we are essentially talking of sodium, potassium and so on and so forth, okay, which are metal impurities, positively charged metal impurities. Okay. If you have this, then you will always have again a hysteresis, and that will be a clockwise hysteresis. It also becomes clear why that is the case. First of all, when we say mobile ion charge, what it means is that I have this MOS capacitor, there is an oxide here, okay. This is our SiO2. Now, this oxide is contaminated with this mobile ion. So, these mobile ions can either move to this interface or move to this interface depending on your voltage on the gate electrode. When I have negative gate electrode voltage, all these charges will move away from the silicon interface to this interface. Remember what we said last time, the charges which are closest to the interface have the maximum effect on CV. In fact, if the charges are out here, they have absolutely no effect on CV characteristics. Okay. On the other hand, if I have a positive voltage, then all these charges will be repelled because of the positive gate voltage, and they will all move to this interface. But again, this movement you see takes time, it will not respond instantaneously, and that time is also in the order of a few seconds. So, now just imagine what will happen because of this, right. I have this gate voltage and this capacitance curve. Let us say I started with negative gate voltage, and negative voltage, all these charges are here. So, there is no effect felt because of the charge, and the CV will look very good like this. Now, there is a positive gate voltage, and because positive gate voltage will stay there for certain amount of time, all these charges by this time will drift towards this and will accumulate here. So, when I am doing my reverse CV, by this time all these charges would have come here. Now, we have all this positive charge. So, whenever there is a positive charge, the CV will go towards the left, remember that, right. We have discussed all this in the last class. So, when I am doing the reverse CV, the reverse CV will go like this. Again I go here for some time, all these charges will go back now to this electrode. So, when I am doing the forward CV, CV will again come back here, because now it does not feel this positive charge, all the positive charge are repelled all the way to the gate electrode, okay, and hence its effect is not at all felt. So, when you have this mobile ion charge, the hysteresis as you see is clockwise, this is what I meant, clockwise hysteresis, whereas here the hysteresis is counterclockwise, the hysteresis looks like this, there is a counterclockwise sense for this hysteresis, okay. So, as I said, if you have really these mobile ion charges, for whatever reason you may see a clockwise hysteresis, and if you have these slow traps because you are doing different dielectrics on silicon or new substrate, again you may have slow traps that will give you counterclockwise hysteresis. Ideally we should not have any hysteresis, forward and reverse should be exactly on top of each other. That would be the ideal condition. Okay. You could have fixed charge, fast interface traps, but slow interface traps should not be present, and that is where you would essentially need to optimize your process and make sure that your slow interface traps are eliminated from the system. There are two more, rather three more non-idealities that I wanted to discuss. The next important thing is what is called this charge quantization effect. Okay. And more precisely also referred to as channel charge quantization. The charge that you have, and it is especially problematic when you are in inversion condition. Okay. And let us just look at what it is, right. So, this is p type silicon again. Let us say I have positive gate voltage Vg and this is SiO2. When I apply let us say plus 5 volt, I have inverted this and you have lot of electrons here. Okay. This is what we call channel charge. Okay. Now, if you look at in this direction, if you look at the band bending in that direction, okay, what you will essentially have is the following, right. This is your oxide, you have applied a positive voltage to the oxide, okay, and let us say this is your Fermi level here, and there is a band bending which would look like this. Okay. Silicon band has bent and that is why it is p type here and it is n type here. Okay. I have reached inversion condition. Now, where are these electrons? All these electrons are supposed to be very close to this interface. You see, this is oxide, as you know, SiO2, this is silicon, and I have applied a positive gate voltage, and hence that positive gate voltage corresponds to this distance that you have. Separation of these two Fermi levels is essentially the applied voltage, correct. Now, what happens in modern day device, all the nanometric device, right, they have extremely thin oxide first of all, remember, and thin oxide has increased the electric fields, right. Electric field is essentially dependent on voltage divided by thickness of oxide. As you know, we have not really followed constant electric field scaling theory. So, fields have increased, that is one aspect. Oxide field has increased and oxide field is related to silicon field also, right, and the silicon field not only depends on the oxide thickness, but also depends on the doping concentration. If you have a high doping concentration, the depletion width is small and you are dropping that voltage, whatever silicon voltage, over a very narrow distance, and that exacerbates this, and hence the fields will be large in silicon. And if fields are large, remember we have discussed this, electric field is gradient of band bending, correct. We have 1 over q d by dx, correct. That is, this band bending that we have, how fast is this band bending, or the gradient of this band is directly proportional to electric field. If we have higher and higher electric field, these bands bend more and more sharply, something like this, very sharp band bending, indicating that fields are very large. Now, something interesting happens, and that is the electrons which are here, they almost looks like a particle in a box, right. In other words, what we mean by particle in a box is that if we have a potential well and if you put electrons in a potential well, this electron cannot take any arbitrary energy, right. The energy of this electron will be quantized. Okay. There are only certain modes that are allowed, because the wave function of the electron should go to 0 at these points, because there is a huge energy barrier. Electrons cannot really exist beyond this point based on the wave nature, okay, and that will quantize the energy. Electron can only take discrete energy, it cannot take continuous energy, okay. In other words, what happens here, this is almost like this, not quite, it is not like a rectangular potential well, but nonetheless it looks like a potential well, and hence the energies of the electrons will be quantized, and what it means is that the number of states available that goes down, and hence the number of carriers will also go down, right. We remember the total number of carriers is probability of the occupancy, which is governed by the Fermi-Dirac statistics, multiplied by the number of allowed energy states. And what is happening because of this quantization, earlier any energy was allowed for the electrons, now there are only fixed energy levels that electron can take, and hence this is a phenomenon that is called inversion charge quantization or channel charge quantization, which reflects as if your threshold voltage of the transistor increases effectively. That is one aspect, that is not the end of the story. There is also, remember, the semiconductor capacitance in inversion, we said dq psi s by d psi s, okay, and of course there was a negative sign here, and we said in inversion for a small change in potential there is a large change in electron concentration, and hence when we had this equivalent combination of C ox in series with C silicon, we said C silicon is infinity or very large compared to C ox, okay, and hence the net capacitance becomes C ox in inversion, right. But now that is no longer the case for two reasons. C ox itself has gone up because C ox is epsilon ox by T ox, because T ox went down, C ox went up, right, that is one part of the story, and Cs will not be very large because the dq psi s by d psi s will not be large because there are only finite allowed energy states. For a small change in the surface potential, the electron charge will not change as rapidly as it would have earlier, right, and hence it degrades your inversion layer capacitance, okay. That is, if you are doing a CV measurement on a transistor, right, this is very important in the context of MOS transistor, your high frequency or low frequency both, remember I said, will give you a curve which looks like this, wherein this maximum capacitance is C ox, okay. Now in presence of channel quantization, charge quantization, your maximum capacitance in inversion will be degraded like this, it will be less than C ox, okay. It will be less than C ox because C ox is in series with C silicon, C silicon is not infinity now, it is finite capacitance, and that will degrade the series combination, okay, and effective capacitance will go down, okay. So this is a very important manifestation that happens in most of the devices today, okay. It could also happen in accumulation to some extent, but in accumulation the band bending is not as much as it would happen in inversion, okay, and the effect in accumulation is not as severe as one would see in inversion. Maybe in accumulation there is a very small effect, may not be as big an effect as you would see in inversion, okay. So this is the CV curve in a transistor. Anyway, if you are doing a CV curve on a capacitor, capacitor will anyway show up like this, but inversion capacitance will anyway be not at C ox, it will be much lower, governed by the depletion bit, maximum depletion bit, but accumulation capacitance may have some impact, okay, it may sort of degrade a little bit, okay. So this is one other important consideration that one has to, people also model this effectively as if saying, your effective oxide thickness has increased and hence your capacitance will degrade, okay. And that is why when we do the oxide thickness extraction using CV characteristic, we call this oxide thickness as an electrical oxide thickness, not a physical oxide thickness. Your electrical oxide thickness extracted from CV curve may not be exactly equal to your physical oxide thickness, and this could be one of the reason why your electrical oxide thickness will be a little different from physical oxide thickness. What I mean by electrical oxide thickness is that I take this capacitance value and I say, okay, look, this capacitance or accumulation capacitance is epsilon ox epsilon naught A by T ox, okay, and I know what is my A, I know what is my epsilon ox and epsilon naught, I have measured my C and I will calculate my C ox. Okay. This kind of oxide thickness calculation is what is called electrical T ox as opposed to physical T ox. Invariably in today's devices, electrical oxide thickness could be anywhere from about 4 to 6 angstrom more than physical oxide thickness, and one reason is this, and the other reason is what we call a polysilicon depletion effect. Okay. So, that is one other non ideality okay. But this effect does not exist if you have a metal gate capacitor or a metal gate transistor. Metal gate transistor, this will not be there, this will be there only if your gate is polysilicon. Okay. Now 45 nanometer and beyond, mostly we are using metal gate transistor, okay, that this is a moot point in that case. Okay. And the only thing that you worry about is channel charge quantization, which may affect your equivalent electrical oxide thickness because you have ultra thin oxides. Okay. Polysilicon depletion is the case, just for completeness, let us also look at what it is. You have p silicon and this oxide, and this is polysilicon. Okay. And this polysilicon is supposed to be doped with, if it is a N MOS kind of a transistor, this will all be supposed to be N plus, heavily doped N plus. Okay. But let us say for some reason it is not very heavily doped. Okay. If it is not very heavily doped, it is more like N minus. Okay. If it is like N minus, and let us say I have applied positive voltage, what will happen if I apply positive voltage? It is as if I am applying a reverse bias to this PN junction. This is at ground potential and this is at positive potential, and that will create a depletion region here, correct. Like a reverse bias PN junction, you have a depletion width, as you increase reverse bias, your depletion width starts increasing. Okay. And because of that, this poly depletion under positive voltage, not under negative voltage, under positive voltage, it adds a new capacitance in series. Earlier my model was only oxide capacitance in series with silicon capacitance, but now I have what is called a C poly capacitance. Ideally that poly was supposed to be a metal like electrode, but it is no longer, because it will add a capacitance here, and hence again the total capacitance will degrade because of that, because as soon as you start putting capacitances in series, your total capacitance starts coming down. Okay. So, even under polysilicon depletion, what you will see is, again let us just look at the transistor structure. This is accumulation. In inversion, ideally you should have had something like this, correct. But as I start applying positive voltage, higher and higher positive voltage, more and more depletion effect. So, very interestingly your curve starts looking like this. Okay. It will never reach C ox, it will start degrading, and when I start, again this measurement is done on a transistor, not on a capacitor. If it is done on a capacitor, anyway the minimum capacitance in inversion is C minimum, that we will not worry about it right now. Okay. But in a transistor structure, the capacitance in inversion should have been oxide capacitance, correct. But no longer the case, because when I start putting positive here, there is a poly depletion, this depletion effect increases, larger the depletion, lower the capacitance, and hence the series capacitance starts degrading, because this capacitance is pulling everything down. Okay. So, this is also not desirable. In fact, one of the reasons why we moved away from polysilicon gate to metal gate was precisely this. I told you a couple of reasons. One is the resistivity. When I have this long finger, poly finger, that contributes RC delay, and hence I wanted to sort of, that resistance is also because you are not able to dope it very well. Okay. In addition to that, you also have this kind of a poly depletion, and your on current of the transistor will suffer very dramatically because of that. Okay. Because remember, your on current of a transistor is directly proportional to your oxide capacitance in inversion for a transistor. if your oxide capacitance in inversion degrades like this in polydepletion or degrades like this in channel quantization, that will degrade your on current of a transistor, and that is why we say your threshold voltage has now increased, because your on current has decreased accordingly. Okay. So, this is one other very important non-ideality that we want to keep in mind, and again as I said, in a metal gate transistor this is not an issue, right. So, the one last non-ideality that I want to talk about is during the measurement. This is all related to the device structure, okay. But during the measurement you may have what is called a series resistance effect or a parallel resistance or parallel conductance effect, okay. And sometimes we rather than calling it R parallel, we call it G parallel. Now, what is it? How do you do the CV measurement? Let us just take high frequency CV measurement, right. It is very simple, as I have mentioned. Anyway, you have a DC bias, let us not worry about DC bias right now. I apply some AC voltage which has some magnitude and an angle theta, okay. Let us say this is my reference and I make this theta as 0 degree, okay. I am just representing it in a phasor form, and I have my device under test which we call DUT, okay. And what you do is measure this current and its angle, right, theta. It is a phasor, right. All you are doing is that you have this device under test, you are applying some input excitation, you are looking at what current is coming out, okay. And then you say, look, my Z is essentially V divided by I theta, correct. And all that equipment is doing is measuring this current phasor that is coming out at the output, and it knows what voltage phasor it has applied and taking the impedance as V divided by I theta, okay. This is the impedance that you get, which is essentially mod Z and angle phi. Let us say it has certain angle and it has certain magnitude. Now, if it is an ideal capacitance, no issue, right, because the angle will be 90 degree, and whatever magnitude you have, it is capacitance, it is 1 over j omega c is its impedance, right. The magnitude, and your equipment has some routines, it will spit out a capacitance value for you. But as a user, you need to tell the equipment whether the device under test looks like a series RC combination because of non-idealities. This is your MOS capacitor that you are trying to measure, device that you have built, or it looks like G parallel and see whatever MOS capacitance that you have, okay, that you have built, okay. Meaning that it has to resolve this Z into either this form or into this form. Z is same, but when it is resolved into this form, you get a different number for resistance and different number for capacitance. When you take the same Z and resolve into this, you get a different value of resistance and different value of capacitance. As I said, if there was no non-ideality, then you get 0 resistance here and the exact same value of capacitance. The capacitance here, if it is let us say 100 picofarad, you get 0 resistance. If you resolve it like this, you get infinite conductance here, okay. It is like an open circuit, this branch is open circuit if it is an ideal capacitance, and you get the same 100 picofarad here, right. This is only if there are no other external non-idealities, external or internal. Now, you see, when you are doing this, there may be a series resistance because you have not probed it properly, if you are not very careful. There could be this cable that you are connecting to equipment, and that may also have some resistance, okay. And the metal that you have used may not be very good, that may also contribute some series resistance. All these are sources of series resistance. What are the sources of parallel conductance? If you have ultra thin gate oxide, then the gate oxide will also leak because of the direct tunneling current that we talked about. If you have a thick gate oxide, there is absolutely no leakage through that. But if you have an ultra thin gate oxide, as I said, let us say 1 nanometer gate oxide, and you have built this MOS capacitor, there is always a leakage here, there is a DC path, correct, and this essentially is showing the DC path. Okay. So, as a user, for example, if you have made sure that there are no series resistance, invariably the rule of thumb is that if you are dealing with a MOS capacitor which has reasonably thick insulator, which means let us say 10-20 nanometer, and you have actually verified by doing an IV measurement that there is absolutely no leakage, then you never use this model, okay, because there is no leakage path anyway. There is no leakage path, meaning this model is true. So, at no point in time it allows a DC leakage current here, whereas this model allows you a DC leakage current to be modeled, correct. That is what we are saying, the device under test has to be modeled properly. So, thick oxide, use a series model always, because no leakage. Okay. And you verify, you can always verify, you can do a very simple IV measurement on this MOS structure and make sure that there is no leakage current, or even if there is a current, let us say picoampere or 10 picoampere, you have a terahertz, tera ohms kind of a resistance which has almost like an open circuit. So, you do not worry about this, but there could be some series resistance, you model it like that, then you get the right value. On the other hand, if you are dealing with let us say less than 1 nanometer kind of SiO2 or an high K dielectric which is very crappy, you are developing a high K process, ideally high K process, if you have a 5 to 10 nanometer, it should have 0 direct leakage current, but for some reason you really have large leakage, which you can always verify by doing a simple DC IV measurement, okay, then you better use this model, because there is always a DC conduction path, and what it means is that the current that you are measuring has a DC component also. You tell the equipment that this is a more realistic model to use, not this model, right. If you do not follow this, then you will actually get an incorrect result for your capacitance. Okay. In fact, I will leave this as an exercise, you can actually do it yourself, that if you were to do this kind of an equivalence, you see that when R is not 0 and this is not infinity, your capacitances in these two cases will not be equal, right. For the same Z, you will get two different capacitance value, okay, and that is when you have to decide, okay, what is the value to choose, and that depends on what additional information that you have on your device, okay, and you need to be careful about that non-ideality, okay. And more specifically, if I may sort of elaborate it very quickly, if you have let us say series resistance only, let us say this is my ideal CV curve, HFCV curve, which I should have got, okay, right, when your RS is equal to 0 and accordingly your R parallel is infinity, okay. But if RS is not 0, then if you are doing the CV measurement, what will happen is that in the low capacitance value range, the effect will be not as great, but when the capacitance is very large, you will actually see a degradation of the capacitance. That is, if in reality, now this is RS non-zero, okay, but you have told the equipment that RS non-zero, meaning this is how the model should have been, this is your actual capacitance that you wanted to get, but by mistake you have told the equipment that use this model, that there is effectively it looks like this, and there is a parallel resistance, and my DUT is this, you extract this value from Z. If it extract this value, your capacitance will be less than what it should have been, but if you use the right model, then you will get back the same capacitance, right. In fact, when you do the measurement, right, of course if RS is 0, the ideal, then there is no issue, but non-zero RS or conductance, whenever you ask the equipment to do a series model and parallel model, you see that the two CVs will be entirely different, right, and you make sure that you do the right representation for the device and you get the right capacitance, right. So, that is a important message that I wanted to convey. Okay. Okay, so let us look at now this issue of parameter extraction from CV. Okay. What I mean by parameter extraction is I want to extract what is my oxide thickness, let me call it electrical oxide thickness, what is my substrate doping, what is my fixed oxide charge, what is my DIT, and so on and so forth, right. These are the most important parameters that you want to. A very simple thing that you do is that you make a MOS capacitor, you do a high frequency CV, and you should make sure that you get a true high frequency CV. Okay. The frequency should be reasonably large, so that you get a capacitance which looks like this. Okay. And make sure that, I mean, if there is hysteresis, of course that is due to slow interface traps, that hysteresis will only tell you how much is the slow interface traps. Okay. Now fine, so what you do first is that you look at this value, accumulation capacitance, and you say that this accumulation capacitance is essentially due to oxide capacitance. Okay. And you say that this is epsilon naught, the area of the capacitance that you have built, and T ox electrical. Okay. T ox electrical extracted in accumulation region, right. So, this, this, and hence you could extract your oxide thickness. Okay. Once you have the oxide thickness, right, then you can go back to this minimum capacitance, C minimum. Okay. Remember that C minimum is essentially determined by the doping concentration. Okay. It has a strong influence, I mean, doping concentration has a strong influence on minimum capacitance, right. So, first of all, what you have to do is that from this measured C minimum you need to get what is the silicon C minimum, because this measured C minimum is really silicon C minimum in series with oxide capacitance. You see, in other words, whenever you are doing the measurement, what you measure is really always oxide capacitance in series with silicon capacitance, correct. So, you need to first get the silicon capacitance from this, this already, this already, because this is oxide capacitance, you can always get the minimum silicon capacitance. Okay. Now, you also know the area. Once you get minimum silicon capacitance, you remember always we deal with per unit area capacitances when we do calculations, right. So, divide it by area and you get the per unit area capacitance, right, which let me call CS min prime, which is essentially this divided by area, and that is essentially epsilon silicon epsilon naught divided by W max, where W max is the maximum depletion width, correct. So, now this and this is known anyway, and you can extract what is maximum depletion width. Once you know the maximum depletion width, you can find out doping concentration now, because as you may recall, the maximum depletion width essentially is given by, right, when you reach a band bending of 2 phi b, that is when I reach inversion, correct, divided by Q Na, where Na is the doping concentration that I want to find out. However, phi b is also dependent on doping concentration, because phi b is kT over Q ln Na over Ni, but you can solve this equation iteratively, and because you know this, you can extract Na value, right, and hence you find out what is Na value. And this we are doing assuming that the doping concentration is uniform. If it is not uniform doping concentration, then also there is a way to extract doping concentration as a function of depth by looking at the CV characteristics, right. So, the textbooks will certainly discuss that, this is a little more involved, but one can easily do that. but for most of the calculation a uniform doping concentration is a reasonably good estimate, right. Especially when one is doing process development anyway, one starts with a standard silicon wafer which has anyway uniform doping concentration. You do not do any implantation or diffusion which will alter the doping concentration as a function of depth. Okay. So, uniform doping concentration is a reasonably good estimate. Okay. As soon as you get this doping concentration, I can extract what is flat band capacitance. First of all, flat band capacitance in silicon, because flat band capacitance in silicon as you know is epsilon silicon epsilon naught by Debye length LD, or sometimes this is also referred to as lambda d, Debye length. And remember, I told you what Debye length is in the last lecture, that is essentially related to your doping concentration. Okay. So, once you know Na, this is thermal voltage instead of band bending psi s is 0 anyway, we have thermal voltage here, and Na is what is already evaluated, and I can find out this, and everything else is known anyway. You multiply this with area, you get flat band capacitance of silicon. Then you can ask the question, okay, if this is a flat band capacitance of silicon, because it is coming in series with oxide capacitance, what would be the measured flat band capacitance? And that is simply CFB measured is 1 over Cox in series with silicon flat band capacitance, correct. And that will give you what is the flat band capacitance, that would be measured flat band capacitance. What it means is that in this CV curve now I am locating a very unique point which is a flat band capacitance point, and this point on the CV curve gives you flat band voltage, and that is how you obtain a flat band voltage. Okay. Once you know the flat band voltage, you know the flat band voltage as you know is phi ms minus Qf by Cox, correct. Phi ms presumably you know, because you know phi s, because you have obtained doping concentration in silicon, it is easy to find out phi s now. Phi m presumably you know what metal you have put on the gate, and you can take the metal work function as phi m. Phi ms is known, VFB is known already from the graph, and I can calculate what is Qf, correct. So, Qf can be easily computed using this. Okay. So, now I have done Tox, I have done Na, I have done Qf. The next important thing is to measure DIT, which is one of the most important thing, especially if you want to get a very good quality MOS capacitor. So, how do we get this DIT? There are multiple ways one can get this DIT. Okay. So, let us look at different ways of getting DIT. The first thing that you can do is that you can look at only high frequency CV. From high frequency CV you can get DIT, you do not need to do low frequency CV. Okay. Remember our model that we have, I apply a gate voltage on the gate terminal, this is oxide capacitance, this is my channel, and that is the psi s surface potential, this is the surface potential which is changing depending on the applied gate bias, and your silicon capacitance plus interface trap capacitance. At high frequency it is 1 over Cox plus 1 over Cs, because when I am doing a high frequency measurement CIT does not respond, although the stretch out is there, the value of the capacitance will not increase. Okay, this is what we have discussed in the last lecture. On the other hand, in the low frequency it is Cs plus CIT which comes in series with Cox. So, in a high frequency CV measurement, just looking at this I do not have the DIT information. However, remember the stretch out of the high frequency characteristic gives me DIT information. So, what I need to find out is what is that stretch out. Okay. So, how do you do that? Okay. So, let us look at this, right. Your oxide voltage can be written as Vg minus psi s, right, and that is what it is. Vox is equal to Vg minus psi s. Okay. Psi s is a silicon potential. Now, there are two elements in series, total voltage is Vg, subtract the silicon potential, you get the oxide potential. Also Qg, the charge that is put, okay, at any gate bias, remember the stretch out that we are talking about. At any gate bias, when I go from one gate bias to the next gate bias, I give enough time and hence there is a stretch out. So, the gate charge that is put is now Qs and Qit combined. Okay. Qs is a silicon charge which is essentially coming due to the impurities, ionized impurities and electrons, and Qit is a interface trap charge. And now hence I can write Vox is Cox times Qg is essentially Cox times Vg minus phi s, okay, and this essentially is Qs and Qit, and what I am doing here is that you differentiate this equation with respect to psi s, okay, and if you do that, Cox dVg over d psi s minus 1, because d psi s by d psi s is 1, minus dq psi s by d phi s and dqit by d psi s, and what is this? This is Cs plus Cit. Okay. So, Cox is dVg by d phi s minus 1 equal to Cs plus Cit, and hence Cit is Cox times dVg over d psi s minus 1 minus Cs. Okay. This we can rewrite it as, because Vg is an independent variable, I am controlling Vg from the external world, and psi s is a dependent variable, psi s is responding to the change in gate voltage, and hence I am rewriting dVg by d psi s as d psi s by dVg inverse, right. That is all I have done here, it is the same thing rewritten here. Okay. So, Cit is Cox times this quantity times Cs. Now, you see I have a means to figure out dit if I do high frequency measurement. From high frequency measurement, at every psi s, each psi s uniquely defines Cs, remember that, because psi s is the band bending. As soon as you fix the band bending, there is a particular value of Cs, that is it, because that band bending will fix Qs in silicon and that Qs will correspond to certain Cs value. So, at any psi s I know Cs, and if I have already computed Cox, because Cox is measured anyway, that is known to me. If we can find out what is d psi s by dVg at every value of psi s, then I can put that value here and Cs value here and get Cit. If I get Cit, remember Cit is Q dit, and hence I get dit value at that psi s, and hence I can generate dit versus psi s plot. Okay. At different band bending I can get dit. In other words, I am getting interface traps in the band gap very nicely. So, how do you do that from the measured information? So, what you do is the following, right. I need to get this. How do you get this? And to get this, we essentially first we note that, as I mentioned, for any band bending psi s, I can estimate what should be Cs, because there is a very unique mapping between psi s and Cs, and that is essentially based on solution of Poisson's equation. If you solve Poisson's equation, you get Qs, which is semiconductor charge, as plus minus indicating that when it is in accumulation it is positive charge, when it is in depletion or inversion it is negative charge. Okay. Accordingly, psi s is positive or negative, in accumulation it is negative, in inversion it is positive. Okay. So, this expression here, this corresponds to all your charge corresponding to whole charge, this whole charge and also the depletion charge, and this expression corresponds to your minority carrier charge, which is electron charge. I have already found out Na, you see, and I know all other constants, epsilon, silicon, everything. Now, for different values of psi s, I can generate Qs, right. I have given a doping concentration, I have a very unique relation between Qs and psi s. once you know the Qs and psi s, you can very easily get capacitance, because capacitance, remember, is dq psi s, silicon capacitance, by d psi s. Okay. So, all you need to do is that you generate psi s versus Qs, which is here, and you differentiate this. You can write a very simple program to do that. It could be even a Excel program to do that. You put in several psi s value, generate Qs, you do dQs by d psi s, and you have a capacitance. Except if you want to get high frequency capacitance, you ignore this term, because this term is due to minority carriers. We say that under high frequency minority carriers do not respond, and hence I ignore this term, I only retain this term, and I generate CHF versus psi s. Okay. In other words, for different values of psi s going from 0, which is flat band, going towards 2 phi b, which is going towards inversion, I generate all the values of capacitances. So, this is theoretical, right. From theory I have been able to generate this, but this value of capacitance uniquely corresponds, this is my measured CHF versus Vg, I have measured it, but this psi s uniquely corresponds to the same band bending, because only when you have that band bending you will get this capacitance, because it is C aux in series with C silicon, and hence for every capacitance value you have a unique value of psi s, and this unique value of psi s maps to a unique value of Vg. This is your measured curve. Okay. So, for every value of psi s, again you can either do it graphically, but you do not want to do it manually, again a very simple program can be written to do that. Every value of psi s will have a unique value of Vg, and in other words what you have generated is really psi s versus Vg. This psi s versus Vg would be theoretical. I do not really need to worry about theoretical psi s versus Vg, I can also generate psi s versus Vg theoretically. Okay. Forget about this curve. All I am trying to tell you is that by comparing this with the measured CV, I have this psi s versus Vg curve, and because I have psi s versus dVg curve, I can get d psi s by dVg very easily. At any value of psi s, I put a value of psi s, I find out what is d psi s by dVg, and I also find out what is Cs, because it is very uniquely defined for that value of psi s. As soon as I know both these quantities, I know Cs, I put that value here, I know d psi s by dVg, I put that value here, I have anyway measured oxide thickness, oxide capacitance, I know what is CIT. Once you know CIT, you know DIT. In other words, what you have generated for every value of psi s, you have generated DIT versus psi s plot. Okay. And this DIT versus psi s plot gives you the interface density in the band gap of silicon. Okay. And this is what is called sometimes this was first proposed by a person called Terman, and in fact it is also called Terman's differentiation technique. Use this differentiation process of psi s versus Vg, d psi s versus dVg is used in estimating interface trap density. Okay. So, this is one way of doing. So, just by having high frequency CV capacitance you can do this measurement, especially when your trap density is very large, this measurement is fairly accurate. But if your trap density is very low, like 10 power 10, then this kind of a differentiation process leads to some errors. Okay. Then this process will not be very accurate, but for most of the process development, when you are doing a new high K dielectric, your trap density is reasonably large, and you can very easily just do a CV measurement, just high frequency CV, and you can obtain the interface trap density as well using the CV measurement. Okay. There are two other ways of doing interface trap measurement, which we will discuss in the next lecture. Those two measurements will work only if you have a ideal, not ideal, a good low frequency measurement done along with the high frequency measurement. Okay. And that we will discuss in the next lecture. So, just to sort of wrap up, there are multiple non idealities in a CV system. which we discussed, ranging from fixed charge, interface charge, slow traps, right, and we need to deal with these non-idealities. And also there are ways to extract the various parameters from the CV measurements as we discussed today. So, now if you have both high frequency and low frequency measurement, then what one could do is that, as I mentioned here, I will go to this equation, remember this, okay. Then from this equation I should be able to get the interface trap density here, okay. So, how does one do that, right, assuming that you have just the low frequency capacitance, okay. Do not worry about this equation, we will postpone the discussion on this equation for a minute, okay, maybe I was looking at the wrong slide, yeah, maybe let us just focus on this, right. I have measured low frequency CV measurement. Remember that in the depletion region the low frequency capacitance responded to interface states, right. If your high frequency was lower, your low frequency was higher, it would be much higher, because the slow varying signal traps can easily respond to that, and that is why I have this model CS plus CIT. And now CIT can be written as 1 over CLF minus 1 over Cox minus Cs, okay. You have measured this low frequency capacitance, and all you need to do now is that at different psi s you need to find out Cs, and also need to find out a relationship between psi s and Vg. Earlier we found that psi s versus Vg relationship through the differentiation technique, but here we will not do that differentiation, we will actually use an integration technique of a low frequency curve as opposed to differentiation technique of psi s Vg derived out of a high frequency curve. Now we are not looking at high frequency at all, we are only looking at a low frequency curve. So what do we do, right, and this is a generic expression that we have, Cox times dVg by d psi s minus 1 is Cs plus Cit, okay, which is what we derived earlier when we were discussing the CV measurement. Now one can sort of rewrite this equation a little bit, just some algebraic manipulation, right, you sort of take this d phi s on this side, and you have d Cox dVg as d phi s times this, and in other words d psi s is equal to Cox divided by this times dVg, okay. Now what I can do now is that this part, right, first of all if I can express this part as a measured low frequency capacitance, and then I can integrate this whole thing, phi s psi s would be psi s 0 plus integration from Vg naught to Vg of Cox divided by Cox plus Cs plus Cit dVg, right, I mean I am just sort of integrating it. For example, at Vg naught is equal to Vfb, right, your flat band voltage is 0, right. So that is an initial condition, for example, okay, and from that you can actually go to different gate voltages and you do this integration, okay, and you can get different values of psi s as a function of Vg. What I am going to do now is that I am going to rewrite this, right, I based on this capacitance equation 1 over CLF is 1 over Cox plus 1 over Cs plus Cit, okay, and I am multiplying this equation on both sides by Cox, again doing some algebraic manipulation here, okay, and I am simplifying that equation, and what I get is Cox divided by Cox plus Cs plus Cit is same as 1 minus CLF by Cox. This is something interesting, right. CLF is what is measured externally, Cox can always be obtained because it is looking at the accumulation value of capacitance, you can find out what is Cox, right. In other words, this term inside the integral can be replaced by 1 minus CLF measured divided by Cox. So now all you need to do is that put different values of psi s, at these different values of psi s you precisely know what is the value of Vg, okay, and accordingly you also know what is the value of CIT. So, at different values of Vg you know what is the value of LF capacitance that you have measured, and hence you would be able to find out DIT as a function of psi s. Again you are mapping DIT to psi s. Two major differences. One first difference is that the way I computed DIT is from low frequency capacitance, okay, and this is what I used to compute DIT. That is one major difference compared to previous technique. In previous technique only high frequency was used. The second difference also is that to compute psi s versus Vg relationship, earlier I did it using high frequency curve, but now I am doing it with a low frequency curve. So, both these things are done using a low frequency capacitance voltage characteristic, right. That is a major departure here, okay. And hence again this was first postulated by Bogeland, and this is using an integration process to compute psi s versus Vg relationship, and hence the name DIT computation using the Bogeland's integration, okay, to get that psi s versus Vg relationship. One last technique, if you have both high and low frequency at your disposal, okay, then what you can do is that you can use what is called a HF-LF technique, right, meaning that I have measured high frequency capacitance which looks like this, I have measured a low frequency capacitance which looks like this. In this region, which is where your band bending is going from flat band to inversion, that is the region of interest for us, okay, from 0 to 2πb, psi s is going from 0 to 2πb. In this region your low frequency capacitance is higher compared to high frequency capacitance. You can look at this difference and you can get CIT as something like this. You make use of a low frequency capacitance, and the Cs that I had in the previous equation, that can be computed using high frequency capacitance, 1 over CHF minus 1 over C aux inverse. So, the CIT, or in other words DIT, is now computed based on two actually measured values, okay, low frequency value and high frequency value, right, and this is how I get DIT as a function of Vg. At different values of Vg I get DIT, but you really need to map it to different values of surface potential, and in order to get that you still need psi s versus Vg, so that you can, if you get psi s versus Vg, then because you know this you can map this DIT versus psi s, and for that you can essentially use the same Bogeland's integration that we talked about earlier, right. You can use that and you would be able to get psi s versus Vg relationship from the low frequency curve. You do it from the low frequency rather than high frequency, because the integration process will not give rise to too much of noise. Whenever you are trying to do differentiation from a measured curve, you can end up with large noise in the differentiation process, okay. And this is what is called a HF-LF technique, right. So, one can extract this interface trap density either solely by high frequency curve or solely by low frequency curve, or a combined high and low frequency curve, right. So, depending on what you have at your disposal, you can do one or all of these, okay. And this also happens to be one very important parameter extraction process. So, then let us stop here. That sort of completes all the discussion on MOS capacitance characterization, and in the next lecture we will discuss about current voltage characterization on a transistor, okay.